7 jets, symmetrical, sun-facing. None of that should happen. When the first stacked frames came through the monitors on the night of the 8th of November 2025, every law of cometary physics cracked just a little. What should have been a single messy plume of dust and gas had become a geometry, a network of 7 bright lines radiating from one luminous core, some bending toward the sun instead of away. For a moment, even the air in the control room seemed to still, as if the universe itself had held its breath. Comets are supposed to run from light. Radiation pressure and solar wind push their tails outward like weather vanes on fire. Yet the thing in those images, 3I, Atlas, an interstellar visitor born around another star, was leaning into the blaze, breathing jets of material directly toward the source of heat that should have destroyed them. The data came from 3 observers on opposite sides of the planet: Michael Jaeger in Austria, Gerald Riemann in Namibia, and Emanuele Prosperi in Italy. None of them spoke as the first renders appeared. They simply stared. 3 different telescopes, 3 different nights of thin sleep, all converging on the same impossible pattern. The chance of error of atmospheric noise aligning by accident was practically zero. We expected a comet. We found choreography. Each observer had been fighting brutal conditions. The object sat barely 10 degrees above the horizon, just 29 degrees from the solar glare, wrapped in the haze of twilight and a nearly full moon. Under those circumstances, even bright planets blur. Yet here were crisp, distinct filaments of light, converging like the ribs of a lantern. At the center glowed a halo, 500,000 kilometers wide, larger than Jupiter, spilling into space like vapor from a submerged volcano. But the halo wasn't the shock. It was the order inside the chaos. 7 jets evenly spaced, persistent across all color filters: red, green, blue, each one pointing where no comet's breath should go. For a few minutes, the astronomers did what humans always do when confronted with something that doesn't fit. They looked for the glitch: a misstacked frame, a stray cosmic ray, a processing artifact. Then, the emails that followed were almost reverent. Possible anti-tail? Projection artifact? Check solar elongation again. But beneath the technical language ran a pulse of disbelief. Because if those jets were truly sun-facing, then either physics had chosen tonight to rewrite itself, or someone, somewhere, had built a machine that could defy it. Think of what that means. Light from those plumes left 3I, Atlas, less than 8 minutes before striking Earth's detectors, carrying with it the fingerprint of every atom it passed. Carbon dioxide, water vapor, silicate dust. Yes, the usual cometary ingredients, but arranged in a symmetry nature rarely bothers with. Nature is messy. It improvises. This repeated itself. Astronomy is usually a slow science. You measure, wait, measure again. But this night was different. The data felt alive, urgent. Every new exposure whispered the same message. Something organized is moving through our solar system. When dawn broke in Europe, the images began spreading through private chat groups and then across public feeds. Astrophotographers who had spent decades chasing comets could not believe what they saw. 7 coherent jets, faint but precise, aligned as if drawn with a compass. By noon, high-resolution composites were circulating among professional observatories. The consensus: this wasn't an illusion. Every independent dataset confirmed the structure. The only debate was whether to describe it as a network, a web, or simply a pattern we do not yet understand. The numbers deepened the strangeness. The halo measured roughly 500,000 kilometers across, yet the nucleus, the solid body at its heart, was likely no larger than 10 kilometers. That means the visible shell was 50,000 times wider than the object creating it. Energy like that doesn't happen quietly. Something was venting with extraordinary power, enough to throw hundreds of tons of material into space every second. And yet the ejection wasn't random, it was balanced, poised, almost deliberate. Scientists are trained to distrust the word deliberate. It implies intention. But when geometry appears where randomness should rule, language starts to bend under the weight of possibility. Across the Atlantic, a graduate student at Harvard forwarded the images to Avi Loeb, the astrophysicist who had once asked whether Oumuamua, the first interstellar object ever found, might have been a light sail. His reply was brief and electric. Either we are watching physics we do not understand, or engineering we were not meant to ignore. Those words spread faster than the data itself. Within hours, the phrase engineering we were not meant to ignore became a trending headline. Still, skepticism held. No reputable scientist wanted to be the first to cry alien probe, so the discussion shifted to safer ground, ice layering, sublimation, carbon dioxide ratios, anything that could make the anomaly fit inside familiar boxes. But even those explanations had to start from the same uncomfortable photograph. 7 lines of light where physics allowed for one. Pause here. Imagine the scene not through data, but through eyes. A man in a cold dome before dawn, breath fogging the eyepiece, the hum of tracking motors like a heartbeat. He isn't chasing revelation, he's just keeping watch. One more routine night of patience and calibration. And then the first exposure resolves on screen. A faint star smeared by motion, a halo, a pattern of threads converging on a point that shouldn't exist. He blinks, rechecks coordinates. The pattern holds. In that instant, a single human mind becomes the first witness to something no one has ever seen. The universe feels different after that. When the day ended, the data sets from Austria, Namibia, and Italy had been merged into one composite, a global act of curiosity stitched together by fiber optics and disbelief. The resulting image was not spectacular in colour. It was spectacular in meaning, a silent photograph that whispered a question older than science itself. Is this nature? Or is it intention? We do not have an answer yet. All we have is a picture grainy, imperfect, taken under the worst possible conditions that refuses to obey the rules. But every revolution in understanding begins exactly this way, with a picture that shouldn't exist and the silence that follows when it does. 3 observers, 3 continents, 1 identical structure. It began, as many scientific revolutions do, with coincidence, except this time, coincidence refused to fade into noise. The night of the 8th of November 2025 wasn't meant for discovery. It was meant for confirmation. All 3 astronomers, Michael Yeager, Gerald Raymond, and Emanuele Prosperi, were simply double-checking a known target, catalogued months earlier as an interstellar comet, 3I, Atlas. Each of them pointed their telescopes toward a patch of sky barely clinging to darkness before sunrise. Each of them fought the same impossible odds, low elevation, thin atmosphere, lunar glare. And yet, when their images aligned, they saw the same thing. 3 eyes looking at one mystery, and the mystery looking back. Austria, Namibia, Italy, 3 dots on a globe separated by oceans and hours, connected by the quiet persistence of curiosity. Yeager's observatory stood amid alpine air, the cold so clean that every sound felt sharpened. Raymond's sky over Namibia burned with desert clarity, stars unblinking above dry plains. Prosperi, operating from a hilltop in northern Italy, they watched the dawn creep up the horizon like a slow-motion tide. They did not plan to observe together. They simply shared a common habit, checking the night's targets before sleep. What they captured would bind them for the rest of their lives. At 4:10 UTC, Yeager's first exposures began, 24 frames through a green filter, 35 seconds each. His camera clock ticked quietly, 1 image at a time, while the world below remained unaware. The signal was faint, barely distinguishable from the background glow, but when he began stacking the images, aligning each frame so that the object sat in the same pixel position, the noise dissolved. What remained was unmistakable. A nucleus surrounded by filaments, 7 distinct ones forming what looked like a mechanical bloom. He checked focus, checked tracking, reran calibration. Nothing changed. Half a world away, Raymond was doing the same. His equipment, a Newtonian reflector under the southern sky, recorded data through dry air undistorted by moisture. When he processed his stack later that night, he froze. His image showed the same symmetry, same directions, same sun-facing jets. Hours later, prosperous data set from Italy landed in the shared network. Despite a thinner atmosphere and heavier light pollution, his stacked image told the same story. 3 telescopes, 3 locations, 3 different sensors, and yet their results overlaid perfectly, like 3 witnesses describing the same impossible event from opposite sides of the planet. If one observer had seen it, the explanation might have been a glitch. If 2 had seen it, maybe a shared calibration error. But 3, under independent skies, using different optics and filters, That is how science draws its first solid line under a question mark. To understand why this matters, you need to know what image stacking really is. In astronomy, the sky is mostly noise, random photons, cosmic rays, and electronic interference. A single exposure reveals almost nothing. But take dozens, align them precisely, and the noise averages away while the real signal grows stronger. It's like listening to the same whisper 50 times until the words finally emerge. That's what these three observers did. Each exposure is a heartbeat, each stack a meditation on patience, and out of the static came something too clear to ignore. The result was circulated through the amateur-professional bridge that defines modern astronomy, a digital thread connecting backyards to observatories, hobbyists to scientists. Within hours, the image reached data forums, Slack channels, and eventually the inboxes of professionals at ESO, NASA, and Harvard. The responses came slowly at first. Polite disbelief, cautious acknowledgement, then an undertone of excitement that nobody wanted to name out loud. Confirm structure. Cross-check with independent observers. Possible multi-event activity. Translation. This might be real. The following day, Prosperi performed a verification run. He re-aimed at 3I, Atlas, using a different telescope, a smaller aperture, a different mount, different filter set. Same outcome. The geometry persisted. That's when the tone of the private messages changed from, could this be noise, to what does it mean? Data consistency is the language of truth in astronomy. When three instruments under opposite skies speak the same numbers, skepticism bends into attention. The odds of 7 identical artifact streaks appearing across independent optical systems are astronomically small. And yet, even as confirmation built confidence, the question grew heavier. What mechanism could produce such symmetry? Jaeger kept a handwritten log. One entry reads simply, jets visible in green, red, and blue. No rotational smear. Pattern stable. Uncomfortable. Uncomfortable because every training, every textbook, insists that comets behave like chaos. One vent here, another there, each flaring unpredictably as sunlight hits. The universe loves entropy. It rarely paints with rulers. But this thing, this visitor from another star, was behaving like it had instructions. In the days that followed, the three men became reluctant colleagues. They cross-calibrated images, compared telescope parameters, corrected for atmospheric distortion, and even inverted the color data to test if the pattern reversed. It didn't. They shared notes on focal ratios, pixel scales, and signal-to-noise thresholds. Every test that should have erased the pattern only sharpened it. By the end of the week, the data had become something larger than any of them, a collective observation stitched together by trust. The same trust that underpins every scientific discovery. If independent minds, working separately, arrive at the same impossible conclusion, the universe is asking us to listen. It's tempting to dramatize the moment to imagine excitement, shouting, celebration. But that's not what happened. What happened was quieter. Long silences between lines of code, slow exhalations as graphs converged, a realization shared not through words but through the stillness that follows them. When they finally uploaded the composite image, Austria, Namibia, Italy layered into one frame, they labeled it with the simplest description possible. Confirmed, jet structure, 3I, Atlas. The 8th of November 2025. No exclamation points, no declarations, just data. Because the deeper the mystery, the calmer scientists become. Weeks later, when professional observatories reviewed the raw files, they reached the same verdict. The jets were not artifacts. They were features. Real, bright, consistent. In a single night, the improbable had crossed into the undeniable. And so, the focus shifted. The question was no longer, is this real? It became, what kind of reality makes this possible? The night of November 8 had proven one thing beyond argument. The anomaly existed. The object was not misbehaving pixels. It was a matter. It was motion. It was something out there, and it wanted to be seen. It was 29 degrees from the sun, 10 degrees above the horizon, twilight pressing in, moonlight floods the sky. And still, the jets appeared. There are moments in science when discovery isn't about what you see, but what you shouldn't be able to see at all. That night was one of them. In astronomy, light is both messenger and enemy. Every photon carries information, but too much light blinds you to what you're trying to find. Observing something that close to the sun is like trying to watch a candle flicker beside a welding torch. The observers knew that. They also knew the odds were against them. The atmosphere thickens near the horizon, scattering and bending light until stars blur into streaks. The full moon adds a veil of background glow, drowning faint objects in silver noise. Yet 3I, Atlas shone through it all, thin and defiant, an object that refused to hide. Jaeger's log notes it plainly. 29 degrees solar elongation, object low, strong gradient, still visible in R and G. In other words, even when physics said no, photons still found their way home. He used narrowband filters: green to isolate diatomic carbon, red for dust reflection, blue for the faint plasma tail that shouldn't have been there. Through each filter, the pattern persisted. The atmosphere could distort shape, could smear edges, but it could not invent symmetry. To the untrained eye, the images looked unimpressive, grainy, faint, washed by glare, but behind those pixels lay a triumph of patience and precision. Each frame had been taken at the razor's edge of possibility, a game of millimeters and seconds where the smallest vibration could erase hours of work. In the control software, tracking graphs wavered like heartbeats. The telescope compensated for Earth's rotation in real time, sidereal speed, adjusted every few minutes as the object crawled toward dawn. Every 20 seconds, the observer checked focus and recalibrated against background stars that were barely visible. The air shimmered. The image danced. But amid that chaos, the structure held steady, as if the object itself were resisting distortion. Even the atmosphere couldn't make it disappear. Meanwhile, in Namibia, Raymond had an advantage. Thin, desert air, one of the clearest skies on Earth. Yet even there, the angle was brutal. The comet's position placed it in a zone of extreme glare, where only the most experienced astrophotographers dare to point their optics. The risk wasn't just wasted time, it was damage. Direct sunlight scattered through a telescope can burn a sensor in seconds. But curiosity overruled caution. He narrowed exposure to the bare minimum, just long enough for the faint halo to emerge. No flare, no ghosting, no error. The structure appeared again. Hours later, Prosperous Observatory in Italy repeated the impossible. A humid sky, heavy with haze, still surrendered the same image. To understand why this stunned professionals, consider the geometry of twilight. The sun, though below the horizon, floods the upper atmosphere with scattered light. That scattered light behaves like fog. It fills the sky evenly, making faint objects effectively invisible. You might detect a planet or a bright comet, but an interstellar body with jets 100,000 times dimmer than the moon? Statistically impossible. And yet there it was. The detection itself became a kind of paradox. Too dim to be visible, too bright to be chance. Something about those jets amplified their signature. Perhaps high reflective dust, perhaps ionized carbon, catching solar rays at just the right angle, or perhaps something else. As Jaeger wrote later, there was noise everywhere, but the pattern stayed clean, like it wanted to be seen. That sentence would echo through every later analysis, because if the pattern survived conditions, this bad blur, glare, diffraction, humidity, then it wasn't fragile, it was real. By mid-morning the next day, image specialists began running the data through atmospheric correction software, simulating what the object would look like if Earth's air weren't in the way. The result only sharpened the mystery. The jets aligned more precisely, their symmetry undeniable. No known comet had ever behaved this way near the Sunday. Most disintegrate or erupt chaotically. 3I, Atlas, by contrast, seemed disciplined, its plumes organized, its brightness steady. The realization unsettled many. The idea that an object could maintain that structure against the blinding power of the sun hinted at a stability no natural process could easily explain. To the human eye, the sun dominates everything. To see anything near it requires humility and risk. The astronomers, each in their separate domes, stared at screens glowing with light that had survived that journey. Sunlight bouncing off something that refused to obey. Their eyes burned from fatigue. Their instruments groaned under the heat, but they stayed. Because the image felt like a conversation, and the sky, for once, was answering back. It shouldn't exist, but it does. The early data reviewers at the European Southern Observatory were skeptical. They ran simulations of atmospheric distortion, asking, could refraction create the illusion of symmetry? Answer: no. The distortion introduces chaos, not order. Next, they tested for camera ghosting reflections inside the optics that can mimic faint streaks. Again, the alignment failed to reproduce the observed geometry. Each failed test narrowed the gap between disbelief and truth. Every explanation that didn't fit only deepened the silence that followed. By nightfall, a subtle shift occurred among the astronomers themselves. Doubt didn't vanish, it evolved into vigilance. They began speaking less about error, more about endurance. How long could they track it before it slipped behind the sun entirely? How many days of data could they salvage before the object disappeared into solar glare forever? The countdown began. Every evening's sky was a race between curiosity and daylight. To the rest of the world, this might sound like an overreaction, scientists obsessing over a blur, but for those who have spent lifetimes staring into noise, clarity is sacred. It is earned in fragments, photon by photon, and when something this faint burns through the brightest part of the sky, it isn't just seen, it declares itself. Twilight, moonlight, haze, none of it mattered. 3I, Atlas wanted to be witnessed. Comets run from the sun. This one leaned in. Every known rule of celestial behavior says sunlight drives comets away. Pressure from photons and solar wind forces dust outward, tails stretching behind them like surrender flags in the solar breeze. But 3I, Atlas, broke formation. Its brightest plumes weren't trailing, it was facing forward, like a swimmer breathing into the current. To the instruments, it looked as if the sun itself were pulling on invisible threads, and the object was answering by pointing straight back. The anomaly first appeared in the early spectrographic analyses. When researchers plotted the jet vectors relative to solar azimuth, the angles came out wrong. The largest jet wasn't anti-solar. It was sunward, a violation so simple, yet so impossible, that several analysts assumed a sign error, someone must have inverted the coordinates. But they hadn't. The data were consistent across all three observer networks. 7 primary plumes, 2 of them bending directly toward the sun, not away. No optical illusion, no misalignment. The math refused to flip. And so began what astronomers quietly called the reversal problem. To grasp how radical this was, remember how comets normally work. The sun warms the nucleus, sublimating volatile ices, mostly water, carbon dioxide, and carbon monoxide. Gas jets outward, dragging dust along, forming the coma and tail. Radiation pressure then sweeps that material away from the sundae. It's a simple equation. Energy in, motion out. Yet 3I, Atlas mocked the equation. It didn't recoil, it advanced. Its jets seemed magnetically tethered to the very star they should have been fleeing. In high-resolution sequences from Namibia and Chile, the forward-facing filaments brightened as solar wind intensity increased, as though responding, not retreating. One analyst described it in a private forum. It's like watching fire blow into the wind and refuse to die. Theories arrived quickly, each more desperate than the last. 1. The projection illusion. Maybe the jets only seem to point sunward because of perspective. But 3D modelling from multiple latitudes killed that theory, the geometry stayed consistent. 2. The anti-tail hypothesis. Some comets exhibit temporary anti-tails, visual effects where dust trails appear to point toward the sun due to orbital alignment, but those effects occur only briefly, usually weeks after perihelion. 3I, Atlas, displayed its sunward structure before, during, and after. 3. The magnetic draping model. Perhaps solar magnetic fields were bending plasma around the nucleus, shaping apparent jets. Yet the curvature was too orderly, the symmetry too stable. Draping creates fluid arcs. This was scaffolding. Each answer tried to save physics, but the image kept erasing explanations faster than they could be written. By late November, the researchers began plotting the object's acceleration using data from the JPL Horizons database. What they found made the violation worse. The trajectory wasn't behaving like a free-falling rock. Something was adding a gentle, steady push, an extra 0.02 millimeters per second squared, unaccounted for by gravity or outgassing pressure. A push with no plume, no heat signature, no visible engine. That combination, sunward jets plus silent acceleration, was the kind of pairing that forces scientists to whisper, because it looked less like a natural reaction and more like control. Meanwhile, public fascination exploded. Headlines screamed, "Comet with reverse tail defies physics!" Comment sections filled with theories, magnetic anomalies, alien thrusters, or solar mirror arrays. Professional astronomers tried to calm the storm, reminding everyone that extraordinary claims require extraordinary evidence. But quietly they were asking the same forbidden question: what if it isn't running away because it isn't afraid? On November 14, the European Southern Observatory compiled the multi-night dataset into a single composite model. When rendered in 3 dimensions, the jets formed a flower-like pattern, 6 around a central axis, 1 vent at the pole, all aligned within 5 degrees of each other. The polar vent unmistakably faced the Sunday. That pattern made some scientists think of engineering, others of ritual symmetry in nature, hexagonal storms on Saturn, snowflake geometry, self-organization at cosmic scale. Still, none of those examples points toward their source of destruction. 3I Atlas seemed to crave sunlight. It leaned in as though feeding from it. The plasma readings complicated things further. Spectral analysis revealed unusual ion ratios, high carbon monoxide, but surprisingly low dust emission. Normally, the more gas released, the more dust follows. Here, the gas was pure, the dust minimal, almost as if the jets were designed to stay clean. Clean jets meant less mass loss, longer endurance, and more precise thrust. The pattern was beginning to resemble something functional. At Harvard's Galileo project, Avi Loeb's team reran the models using a hypothetical, directed venting array, a configuration of nozzles capable of steering by coordinated gas release. Their conclusion was cautious. If such a system existed, its behavior would match the observed acceleration without violating conservation laws. Translation: physics works if intelligence is added. And yet, even with mounting evidence, no one could say the words artificial in an official paper. The journals wouldn't allow it. The field wouldn't tolerate it. The safest phrase became non-gravitational perturbation, a label that sounds scientific but means we have no idea what's pushing it. For the observers themselves, the experience was less theoretical and more emotional. Each night, they watched the object draw closer to the sun, expecting it to fragment under heat like every comet before it. Instead, its halo contracted, became sharper, its form simplifying under pressure, as if aligning for something. The closer it came to danger, the more organized it became. It behaves as if sunlight is not its enemy but its signal, one astronomer wrote in his notes. In the weeks that followed, the sky watchers noticed something even stranger. A second, fainter line, extending opposite the primary jets. A tail that did point away, but faint, subdued, almost ceremonial. It was as if the object acknowledged the laws of nature, then chose not to obey them. 2 tails, 2 directions, 2 stories written in light. One followed the rules, the other wrote new ones. By early December, as it skimmed its closest approach, 3I Atlas had earned a new nickname in quiet observatory circles, the reversal, because it wasn't just turning its jets toward the sun, it was turning our understanding inside out. In the end, every telescope agreed on the same picture. The solar wind roared outward, the plasma field streamed around it like invisible rivers, and the object, small, cold, precise, held its face to the fire and didn't burn. Most comets burst, flare, die. This one is organized. At perihelion, its closest pass to the sun, 3I Atlas should have come apart. The heat, the radiation, the magnetic turbulence, all of it conspires to turn comets into dust. Every rule of cometary life ends the same way: sublimation, disintegration, silence. But 3I Atlas refused to follow the script. As it neared the 29th of October 2025, the day of closest approach, telescopes across Earth prepared for a spectacle. Astronomers expected chaos brightening, jets whipping outward, maybe even a visible breakup. The solar wind that week was fierce. A coronal mass ejection had erupted just days before, filling space with high-energy plasma. Instead of disintegrating, the object did something no one anticipated. It became simpler. Its sprawling halo, which once stretched over 500,000 kilometers, began to shrink, not vanish, but condense, tightening like a pupil adjusting to light. The brightness curve flattened, the wild jets folded inward into a clean, symmetrical pattern that looked less like an explosion and more like calibration. As if the closer it came to the sun, the more disciplined it became. This was not a comet gasping in its final moments. This was choreography. Observatories monitoring the object through automated photometry noticed the stability first. The usual flickering that defines a comet's coma, caused by irregular bursts of gas, simply stopped. Light output stabilized to a steady plateau, constant within 0.02 magnitudes for more than 72 hours. That kind of consistency is unheard of for an active comet at perihelion. The data forced a chilling realization. Whatever was happening out there, it wasn't random venting. The coma, that luminous haze of gas that normally blossoms like a dying ember, never came. The object kept its atmosphere neat and enclosed, like an engine keeping pressure behind invisible valves. By now, nearly every major space agency was tracking 3I, Atlas. The European Space Agency, NASA's Solar Dynamics Observatory, and even Parker Solar Probe had their instruments tuned to the region. But none detected the expected infrared flare from dust or water vapor. The thermal signature was too faint. The implication was staggering. The object was surviving the sun's heat with minimal mass loss. That should be impossible for anything composed of volatile ices. If it were ice, it was the toughest ice ever known. If it wasn't ice, then what was it? The first whispers of alarm came not from public institutions, but from private message boards, where astronomers share raw data. One post simply read, "This thing isn't evaporating. It's adapting." Others followed, stability curve abnormal, acceleration still increasing 0.02 millimeters per square second beyond model. Acceleration. Again. The word everyone had been avoiding returned like a ghost. 3I. Atlas wasn't just holding together, it was changing speed. By late October, its trajectory no longer matched gravitational predictions. The deviation was small fractions of a millimeter per second squared, but consistent. The numbers suggested a continuous, directed force acting over days. Normally, such thrust comes from jets expelling material, but there were no visible outbursts. No dust, no flare, no thermal bloom. It was as if the object had found a way to accelerate without thrust. At the Jet Propulsion Laboratory, analysts tried to reproduce the curve. They fed every variable solar radiation pressure, asymmetric outgassing, plasma drag into their models. Nothing matched. Then, one researcher, almost jokingly, added a constant low-level acceleration term, as if simulating a steady engine burn. The trajectory fit perfectly. The room went quiet. "It behaves like it's under control," one of them said softly. They didn't put that in the official memo. The memo said, "Non-gravitational component consistent with continuous low-thrust source." But everyone knew what that meant. Meanwhile, the object's color indices changed subtly. The green glow, typical of carbon chain molecules, diminished, replaced by a faint blue-white hue. That shift suggested the emission wasn't dominated by volatile gas anymore. It was plasma, ionized and structured. An object shedding gas behaves chaotically. An object controlling plasma behaves intelligently. The distinction sent ripples through the astrophysics community. Some argued it could be a new type of interstellar composition metals or crystalline carbon stable, under heat. Others whispered it might be technology, an ancient probe harvesting solar energy instead of fleeing from it. Both possibilities were terrifying in their own way. Through all this, 3I, Atlas, remained eerily quiet. Radio dishes aimed at its coordinates detected nothing, no beacons, no transmissions, no artificial signals. Silence, pure and deep, and yet its motion spoke louder than any message. When plotted frame by frame, the acceleration looked almost intentional. Small course corrections synchronized with solar activity. Each time the sun emitted a flare, the object's vector shifted slightly, as if responding. Cause and effect, but in reverse. Was it reacting to the sun, or was the sun reacting to it? In December, as it moved away from perihelion, the astronomy networks braced for the usual cometary fade, a slow, dimming disintegration, the sigh of a journey ending. Instead, brightness held steady, the coma stayed compact, the object left the sun's sphere stronger than it entered. It was as though it had gone to the furnace not to die, but to charge. No comet had ever behaved like this. None had ever shown discipline under pressure. Most bodies fear the Sunday. This one remembered something in it. By then, headlines were unavoidable. The comet that refused to die. 3I Atlas, accelerating after perihelion. NASA confirms anomaly. But behind the sensationalism lay genuine unease, because when comets survive perihelion, it's by luck, not by order. Randomness saves them. 3. Atlas displayed the opposite. Order saving itself from chaos. The deeper scientists looked, the more coordinated its behavior appeared. The 7 jets, those elegant, symmetrical filaments, stayed perfectly aligned, even as the object rotated. No tumbling, no flickering, just steady illumination, like a structure maintaining balance against solar wind. One researcher at the European Space Agency described it best. It's like watching a heartbeat that never falters, even as the universe tries to stop it. If the story of 3I, Atlas, began as awe, it was now edging toward alarm, because what they were witnessing was no longer an accident of nature. It was resilience, a system maintaining order where disorder should reign. The coma that never came became more than a scientific anomaly. It became a symbol of defiance written across the solar wind, a message made of silence and geometry. Not every visitor comes to burn. It looks natural, but it's acting like it has a plan. Every scientist who stared at the data from 3I, Atlas, wanted to believe in ice. Ice is comforting. Ice obeys rules. You heat it, it sublimates, it vents gas, it spins. No mystery, no message, just chemistry and sunlight. If this were ice, then physics was safe. The first model to calm the panic came from a team in Finland. They proposed CO2-driven jets, not alien engines, just carbon dioxide sublimating through layered crusts of dust and frozen gas. It was elegant, mathematical, and reassuring. According to their simulations, the comet's surface might have formed in alternating sheets. Ice, dust, dust trapping CO2 beneath a brittle crust. When sunlight hit one side, the gas pressure would rise unevenly, escaping through fractures in concentrated plumes. If the rotation was slow and balanced, those plumes could emerge in nearly symmetrical positions. Order, the paper said, does not always require intelligence. Sometimes, it only requires repetition. That sentence became a lifeline. Within a week, half the astronomical community had rallied behind the layered ice model. It explained almost everything. The 7 jets, the apparent symmetry, even the steady acceleration, just the combined push of consistent CO2 release. The only problem? The numbers didn't add up. Spectral data from the VLT in Chile revealed an extreme CO2H2O ratio of nearly 8:1, far higher than any known comet. Even 2I, Borisov, the interstellar visitor of 2019, never showed more than 1, 5:1. 8:1 meant this thing was almost pure carbon dioxide ice, less a dirty snowball, more a cryogenic engine. And then there was the temperature. To sustain that much CO2 sublimation, the surface would have to be far warmer than any solid ice could survive. Either it was venting from subsurface reservoirs, insulated beneath something non-ice-like, or the heat was being managed in ways we didn't understand. Some suggested it was rotating so slowly that sunlight could warm its entire surface evenly, creating synchronized jets. Others argued the opposite, that it was spinning fast enough to spread heat through centrifugal venting. Both could, in theory, produce balance. Neither could explain why the jets stayed constant through changing solar conditions. Nature improvises. It doesn't maintain perfect tempo. Yet 3I, Atlas, pulsed like a metronome. When the Gaia spacecraft's photometric data came in, it revealed another twist. The brightness curve was modulating in a rhythm of 5.9 hours, possibly the object's rotation period. That regularity suggested a solid, cohesive structure, not a loose rubble pile. A solid core meant stability. Stability meant control. Still, researchers held on to hope. They called it coherence of outgassing, an unremarkable phrase for something extraordinary. Maybe the object was just built by nature to endure. To test the idea, the Max Planck Institute created a digital twin, a high-fidelity 3D model simulating layered sublimation under solar heating. They even programmed in random vent positions and variable spin. Out of 10,000 trials, only 4 produced near-symmetrical jets, like those seen in the real data. 4 in 10,000. The model worked, technically, but probability whispered another story. Meanwhile, Parker Solar Probe data confirmed the surrounding plasma environment had been unusually turbulent during the object's perihelion pass. A normal comet would have shown chaotic tail fluctuations. 3. I. Atlas. However, adjusted smoothly, its plumes deflecting in unison as if responding to invisible commands. This wasn't chaos being tamed. It was an order being expressed. In press briefings, scientists avoided poetic language, but their voices betrayed it anyway. One said softly, "It behaves like it's aware of its own heating." Another laughed nervously before adding, "Let's just say it's an overachieving snowball." The laughter didn't last, because the more they studied its composition, the stranger it became. If the CO2 ratio were that high, the object couldn't have formed in any region like our solar system. That much carbon dioxide ice requires extreme cold temperatures, only found in interstellar molecular clouds thousands of light years from here. It wasn't just from another star system. It might have been assembled in the coldest places between them. The thought brought a kind of fragile hope. If nature could sculpt something this precise from nothing but ice and dust, then maybe intelligence wasn't the only way the universe organized itself. Maybe geometry and grace could emerge from randomness, given enough time and silence. Some scientists clung to that interpretation like faith. Others weren't so sure. One late-night thread between observers reads, "If this is just ice, why does it keep aiming? Because the sun tells it where to point, and it listens too well." For all the debates, one fact remained uncontested. 3. Atlas was stable. Its structure held. Its rotation remained constant. Its jets pulsed predictably. In a universe defined by entropy, such cooperation between matter and light is rare, but not impossible. Maybe the object wasn't alive or artificial, it was simply tuned. A frozen instrument built by physics itself to play one perfect note. By December's end, the scientific community had split into 2 camps. The first insisted on naturalism. The layered ice model, however unlikely, must be true. The second whispered about intent, not necessarily alien, just purposeful. The idea that something could exist between nature and design, where evolution and engineering blur into the same law. A third group simply watched and listened, unwilling to choose sides. As one astronomer wrote in her journal, "Perhaps what we're seeing isn't intelligence, but memory physics remembering how to build a pattern." That thought softened the fear, because if the universe can remember beauty, maybe it can also mean no harm. The night sky, once threatening, grew strangely gentle again. The object was still there, a faint glimmer moving away from the sun, leaving no debris, no explosion, just equilibrium in motion. It looked natural, but it kept behaving like it had a plan. And so, between skepticism and wonder, hope returned quiet, cautious, and luminous. 7 jets, near perfect spacing, not what randomness looks like. For weeks, scientists had taken comfort in the idea of ice-layered, volatile, chaotic, yet understandable. But patterns have a way of betraying their origins. The more data poured in, the less random 3I Atlas appeared. By December, the discussion had shifted from what it was made of to how it was arranged. Because those 7 jets, frozen in their elegant geometry, weren't scattered by chance. They obeyed alignment. They obeyed something. When researchers mapped their angular spacing relative to the nucleus, the results startled everyone. Each jet separated from the next by roughly 51 degrees, within a margin of 2. That's not nature's usual handwriting. Natural vents open wherever heat fractures allow messy, uneven, unstable. Symmetry is rare, fleeting, accidental. But here, it was persistent. 7 lines in near-perfect rotation, a geometry pretending to be physics. The team at the Vera C. Rubin Observatory ran orientation analyses using thousands of stacked images taken over weeks. Despite the object's changing position relative to Earth, the angular ratios between the jets remained constant. That meant one of 2 things. Either the vents were distributed around the nucleus with uncanny uniformity, or the jets themselves were being stabilized by some external field, magnetic, rotational, or something stranger. the natural explanation began to tremble under its own weight. If those jets were vents, they should drift as the object rotated, but the light curves told a different story. No phase wobble, no irregular flicker, no shadowing. Instead, the brightness rhythm pulsed like clockwork, 5.9 hours per rotation, each cycle producing the same visual pattern. One astronomer put it bluntly, that's not chaos rotating, that's symmetry maintained. In space, symmetry is suspicious. Stars flare asymmetrically, planets form obliquely. Gravity loves imperfection, it's what makes orbits dance. But machines adore symmetry. So, when the jets of 3I, Atlas, arranged themselves like the blades of a cosmic fan, even the most cautious minds began to hesitate. The axis tilt added another layer to the mystery. From spectroscopic Doppler shifts, scientists estimated the object's spin axis to be tilted only 5 degrees off the ecliptic plane, almost parallel to the Sun's equator. That alignment is astronomically rare. Most comets tumble at random angles, relics of violent formation. 3I, Atlas, by contrast, was practically aligned with the solar system's geometry as if it had entered our plane on purpose. Coincidence? Maybe once, but coincidence after coincidence begins to look like intent. Researchers across observatories began to whisper a new phrase, the symmetry problem. It wasn't official, not in any paper, but it crept into every meeting, every chat log, because symmetry, in this context, wasn't beauty, it was accusation. To prove that the pattern could still be natural, scientists from the Institute for Planetary Physics in Prague built digital models of rotating nuclei with random vent distributions. They let the simulations run overnight, thousands of iterations, each generating light profiles for comparison with the real data. Out of 10,000 trials, none matched the observations. Not one. In all cases, random vents produced drifting, flickering asymmetry. The real 3I, Atlas data, remained steady, poised, repeating itself like a ritual. The modelers added rotational precession, variable gas flow, temperature gradients, every chaotic factor they could imagine. The result? Still wrong. By dawn, the lead researcher wrote only 2 words in his notebook. Not random. At the same time, NASA's Solar and Heliospheric Observatory, SOHO, recorded faint polarization patterns in the dust halo surrounding the object. The orientation of the polarized light matched the 7-jet geometry almost exactly, implying an underlying magnetic structure. If those jets were plasma streams instead of mere gas, they could, in theory, align themselves through magnetic resonance, like iron filings shaping around an invisible field. But that raised another question. What was generating the field? Comets have weak magnetism. Rocks do not organize plasma into 7 arms of symmetry. So where was the order coming from? The search for parallels turned desperate. Some compared the structure to Enceladus, Saturn's icy moon, whose geysers erupt in symmetrical plumes through subsurface fissures. Others pointed to Io, where volcanic vents follow tidal stress lines created by Jupiter's pull, but both examples depend on massive gravitational forces. 3. Atlas was alone, drifting through interstellar space. No planet tugged at it. No moon guided its rhythm. Still, the human mind clings to reason. If geometry appears, we look for gravity. If control appears, we look for coincidence. But as one researcher wrote in a quiet memo, we are running out of coincidences. Photometric data revealed something subtler still. Each jet emitted slightly different spectral lines. The outermost pair glowed richer in carbon, while the central axis displayed a faint metallic signature nickel without accompanying iron. That was the detail that froze the conversation in every lab. Nickel without iron is not typical for cometary material. It's a ratio seen in industrial alloys, not cosmic rubble. The data team double-checked, recalibrated, and remeasured. The signal persisted. If confirmed, it meant the material composition of 3I Atlas wasn't homogeneous. It was selected. By late December, the language of the reports had changed tone. Words like venting and outgassing gave way to array, structure, and distribution. The mathematics remained careful, but the fear had softened into fascination. Maybe we are looking at a natural phenomenon so organized it appears engineered, one scientist offered. Or maybe we're looking at engineering so ancient it appears natural. For the first time, major institutions began using machine learning algorithms to classify 3I Atlas. The models trained on decades of comet and asteroid data failed spectacularly. The AI flagged it as an unknown hybrid, part comet, part metallic body. Even artificial intelligence couldn't decide if it was natural. Night after night, as telescopes tracked it slipping back into darkness, the symmetry held. No drift, no collapse. And that's when doubt stopped whispering and began to speak. What if we weren't watching an object failing to act like a comet? What if we were watching a design pretending to act like one? Science doesn't fear ignorance. It fears patterns that can't be broken, because once symmetry stops being a coincidence, it starts being communication. If you were building a probe, it would look like this. That line started as a joke, whispered in a late-night conference chat among exhausted astronomers. But jokes have a way of surviving when they contain truth. Within days, it wasn't a joke anymore, it was the outline of a hypothesis no one dared publish. Yet everyone was already testing. Because 3I Atlas didn't just resemble something engineered, it behaved like one. Let's start with the structure. 7 primary jets equally spaced, equatorial. 1 polar vent, a configuration almost identical to a 7-point thruster array, the kind used in conceptual designs for interstellar probes to maintain precise orientation under variable pressure. In theory, a distributed array like that could perform continuous microcorrections, rotating, braking, or accelerating without visible exhaust flame. If you wanted to travel between stars, conserving fuel while controlling direction, this is how you do it. Every symmetry has a function. When researchers mapped the vector of each jet, they noticed a peculiar pattern. Small variations in intensity corresponded with slight course changes recorded by the JPL orbital tracker. Each burst of brightness coincided with a minuscule correction, steering the object back toward its predicted hyperbolic path. That's not random venting. That's feedback. The Harvard Galileo project team modeled it under the assumption of intelligent control. If each jet produced a measurable impulse of even 10 to the power of 4 newtons, coordinated in sequence, the object's entire acceleration profile could be reproduced without violating conservation of momentum. No magic, no miracle, just mechanics applied perfectly. For months, the naturalists fought to preserve the old narrative. Gas, dust, coincidence. But their equations began to bend under the weight of precision. Natural systems wander, they wobble. 3I. Atlas did neither. It corrected itself. The trajectory data revealed a motion so exact it seemed scripted. After passing perihelion, instead of veering off unpredictably, the object adjusted subtly, consistently aligning its course with the galactic plane. If this were a probe, that's exactly the path you'd take to minimize gravitational drag from stellar systems. If this were a rock, it's the luckiest rock in the universe. Engineers began to notice the parallels. A veteran from ESA's propulsion division, reviewing the datasets, wrote privately, "If it's natural, it's accidentally doing what we've been trying to build for decades." He was referring to photon sails, thin, reflective membranes that use sunlight for propulsion. A perfect solar sail, if oriented correctly, would lean into the light to adjust trajectory, exactly as 3I Atlas had done. Now combine that with the 7 jets, and you get something more advanced, a hybrid drive, part passive, part active, a craft that uses sunlight as fuel but keeps microthrusters for course correction. If you were building a probe, one scientist said, you'd build this. Public speculation exploded. Alien probe became headline shorthand, but for the scientific community, the thrill lay not in fantasy, it lay in logic. For the first time, engineering diagrams began appearing in academic discussions, comparing the geometry of 3I Atlas with known propulsion concepts. The resemblance was unnerving. Thruster array model, 7 symmetrically placed nozzles at the equatorial plane, 1 polar stabilizer vent, controlled exhaust of CO, 2, or ionized carbon, acceleration near perihelion consistent with planned solar assist maneuver. Even the estimated mass-to-thrust ratio matched designs proposed for long-duration AI probes machines meant to drift between stars for millennia, awakening only near targets of interest. But if it was engineered, by whom and when? Here, the thrill deepened into awe. Because 3I Atlas isn't from here. Its incoming velocity over 61 kilometers per second and eccentricity to 6.14 mark it as definitively interstellar. The stars it might have passed near on its way here drift thousands of light years apart. Any civilization that launched it would have done so before humanity existed. We weren't watching visitors, we were watching ancestors, or perhaps witnesses older than history. Skeptics countered quickly. No transmission, no structure visible, no radar echo suggesting metal. Fair points. But engineers replied with another truth. The best machines don't need to talk or shine. A true probe designed to endure deep time would minimize signature, blending into the cosmic background, masquerading as debris. The perfect messenger, one researcher wrote, would look like a rock until it decided otherwise. And maybe, just maybe, that's what was happening now. The pattern of brightness modulation, tiny variations at regular intervals drew special attention. Amateur radio astronomers noticed that when light intensity was converted into frequency and plotted over time, it formed harmonics, not noise. No one claimed it was communication, but the data carried rhythm, repetition, pulse. One physicist joked that if you played the light curve as audio, it sounded almost like breathing. A machine, exhaling across light years, someone wrote in the comments. Then came the trajectory anomaly that electrified the field. After perihelion, 3I Atlas should have followed a clean outbound hyperbola. Instead, its path flattened subtle, but measurable, almost like a controlled braking maneuver. By December 15, it was officially decelerating, not enough to suggest power, but enough to raise the question that made every astrophysicist's pulse quicken. Why slow down? If you were a machine using the sun for navigation, this was the moment you'd collect data, reorient sensors, or wait for a signal. If you were a comet, you'd just drift. It wasn't drifting. NASA's infrared array searched for thermal exhaust. Nothing. ESA's radar teams found no reflections. Still, the motion persisted, whispering the same logic through numbers. Controlled acceleration, symmetrical thrust, deliberate slowdown, not chaos conduct. To imagine an engineered probe is to imagine intent, and intent implies message. But what if the message isn't words, it's behavior, a silent demonstration, a geometry written in plasma and patience, 7 jets, 1 polar vent, a body that listens to starlight and answers in thrust? That's not fantasy. That's the blueprint. In time, even cautious voices softened. A researcher at MIT summarized the new consensus in a single line. Either the laws of physics have an aesthetic sense, or something with aesthetic sense uses the laws of physics. So, the case for engineering was never declared officially. It didn't need to be. It grew quietly, like gravity pulling minds toward the possibility that the universe had already mastered what we're still learning. To travel without flame, to speak without sound, to last without end. And if this truly was a probe, then it wasn't shouting across space. It was showing us how to look. No visible engines, but it's not just drifting. When the first post-perihelion data came in, astronomers expected to see 3I Atlas speeding away, losing brightness as it escaped the sun's pull. Instead, the opposite happened. The object's trajectory had changed again, fractionally, subtly, impossibly. It was slowing down. The initial notice appeared quietly on JPL's Horizons update feed. Observed orbital residuals suggest deviation from purely gravitational motion. A polite phrase, harmless, almost bureaucratic. But to the few who understood what it meant, it was seismic. A deviation from gravity is no small thing. It's a rewriting of the universe's simplest rule, that what falls must keep falling unless something pushes back. So, what was pushing back? In the numbers, the shift looked trivial, an average deceleration of 0.02 millimeters per second squared. But over millions of kilometers, that was enormous. Imagine a spacecraft thousands of kilometers wide applying a continuous whisper of reverse thrust, gentle enough to leave no visible trace but powerful enough to bend orbits. And yet, no infrared glow, no ion tail, no ejector plume. Whatever was happening, and it was invisible. A body without engines acting as if it knew where it was going and when to stop. The first theory blamed solar radiation pressure. Maybe light itself was slowing the object, pushing against its surface like a cosmic breeze against a sail. But the math didn't hold. Even the largest estimated cross-section couldn't generate more than 1/10 of the required force. Then came outgassing recoil tiny jets of vapor, giving a subtle braking effect, but the direction of the observed acceleration didn't match known vent locations. It wasn't random or reactive. It was coherent, aligned precisely opposite to the object's motion, as though calculated. That word, calculated, made its way into internal memos more than once before being edited out. At the European Space Agency, analysts replayed the timeline frame by frame. In early November, acceleration pointed sunward. Now, in mid-December, it opposed velocity, acting like drag. But there's no drag in interplanetary space, only in tension. Something is breaking, one physicist said quietly in a meeting. Something knows it's time to slow down. Nobody laughed. The Harvard Galileo project ran Monte Carlo simulations of non-gravitational forces, venting, solar wind, and pressure differentials. None fits the precision of the deceleration. When they added a constant force model like that of a controlled engine burn, the match was perfect. Every data point is aligned. It's almost too perfect, the lead analyst admitted, like it's trying to tell us it's deliberate. Outside the labs, speculation reached fever pitch. Alien breaks. Tabloids screamed. But inside, the mood wasn't wonder. It was unease. Because if an object can accelerate without visible thrust, then our understanding of propulsion isn't just incomplete, it's irrelevant. This wasn't breaking physics. It was bypassing it. On December 18, ground-based radar from the Goldstone Deep Space Complex caught a faint reflection, a ghost echo returning from somewhere near the object's last known coordinates. The delay didn't make sense. The reflection came back slightly early, implying the object had moved more slowly than projected, closer than expected. That was confirmation. The deceleration wasn't measurement error, it was happening. And that realization changed everything. For decades, spaceflight engineers have dreamed of propulsion systems that need no fuel drives, that harness external fields, radiation, or quantum effects to push against the void itself. Some called it photonic manipulation, others plasma resonance. None of it worked, at least not for us. But 3I, Atlas, was doing something eerily similar. It was moving through the solar plasma like a bird riding invisible thermals, adjusting velocity with grace that felt almost alive. If it were a machine, it would be the most efficient one ever built. If it was natural, it was performing miracles. Astronomers plotted its new path. Instead of following the expected hyperbolic escape trajectory, the curve bent slightly inward, reducing its outbound velocity by a measurable 2.3%. That doesn't sound like much until you realize it takes power to decelerate in space. The sun's gravity pulls everything in. Nothing slows down unless something acts against it. But here, at the edge of light, a body from another star was braking quietly, deliberately, like a visitor preparing to linger. NASA's Parker Solar Probe, still within the sun's inner heliosphere, recorded a strange local magnetic ripple as the object passed its field of observation. The disturbance was minor, but distinct, a dip in plasma density synchronized with 3I, Atlas's predicted position. To some, it suggested an interaction like a field being manipulated, a localized bubble of reduced resistance, not propulsion in the chemical sense, propulsion in the environmental sense, shaping the medium around it instead of fighting against it. That kind of control implies design, and design implies purpose. As the data circulated, private Slack channels among observatories, filled with cautious messages, were past coincidence. Acceleration is consistent with field coupling. If it's a probe, it's parking. But no one said that aloud at conferences. Not yet. Instead, public statements adopted a vocabulary of evasion. Non-gravitational influences remain under study. Possible plasma interactions are being explored. Further observations required. The words said nothing. The silence said everything, because everyone understood the timeline. Soon, the object would move beyond detection range. Within weeks, it would vanish into the dark, carrying its secret with it. And that's when the fear set in, not of danger, but of ignorance. What if this were the closest we would ever come to understanding an intelligence older than the sun, and we were letting it slip away? Late December nights turned restless. Observers stared at static, listening to empty spectrograms, hoping for a signal, any sign that the object might acknowledge its watchers. Nothing came. Only the faint, unbroken deceleration curve, steady, precise, polite. As if the visitor knew it was being studied, and was slowing down just enough to make sure we noticed. And somewhere in that quiet realization, excitement gave way to unease. Because acceleration can be random, but deceleration means choice. Something had chosen to pause. And in a universe where everything falls, the thing that stops becomes a question. What if this isn't about the object, but about what we see in it? For months, we had treated 3I Atlas as a specimen, a case study, a mirror for physics. But the longer we watched, the more the reflection changed, because what we call data is never neutral. It's shaped by the eyes that gather it. And sometimes, what looks like a mystery in the stars is only the shape of our own need to understand them. When the first images arrived, those 7 jets, the impossible geometry, we projected order onto them, because that's what humans do. Our minds crave design the way lungs crave air. Randomness is intolerable. Symmetry feels safe. Maybe that's why we saw a probe when the sky offered silence. Still, something about 3I Atlas resisted dismissal. It didn't just bend our instruments, it bent our definitions of observation itself. Because what if intelligence isn't always loud or intentional? What if meaning is ambient, like background radiation present, measurable but only heard by those who learn how to listen? Maybe we weren't observing it. Maybe it was observing us through our reactions, our theories, our need for purpose. Throughout history, every unexplained light in the sky has served as a mirror for civilization. In ancient times, comets were omens of wrath or renewal. In the Renaissance, they became portents of motion and mechanics. In the modern era, they became laboratories for chemical truth. Each age saw what it needed most: fear, wonder, proof. Now, in the 21st century, we see technology, because technology is the new mythology. The debate over 3I, Atlas, had already left the realm of science and entered something more fragile: belief. One camp believed it was pure physics, a story of ice, gas, and chance symmetry. The other believed it was a design, a cosmic signal, proof of company in the void. But belief itself became the point, not which version was true, but why we needed either one to be. When philosophers looked at the data, they saw a new version of the Fermi paradox unfolding, not where is everyone, but what if they've been speaking all along, in languages we can't yet translate? Because if the universe were full of intelligence beyond our form, would we even recognize it? Would we see a craft or a comet? Would we read a message or dismiss it as noise? And if they wanted to be found, would they not choose a form we'd already expect to find? A rock, a traveller, something small enough to ignore until we finally learned to notice. Some argued the entire event had nothing to do with extraterrestrials and everything to do with human perception, the psychology of wonder. The object could have been anything. We made it sacred by our attention. Quietly, it became a kind of collective mirror therapy for the species, forcing us to confront how we search the cosmos not just for life, but for meaning. Because every telescope pointed outward is also a telescope turned inward. The strange thing about 3I, Atlas, is how it altered people. Astronomers began writing differently, more poetic, more reverent. Equations gave way to metaphors. Lab notes became confessions. Even the most skeptical voices couldn't help describing it as beautiful. One scientist admitted during a panel, "It's like looking at a mind that doesn't need words." And another replied, "Maybe that's what the universe is, a mind that doesn't need words." The audience laughed, softly, not because it was absurd, but because it was uncomfortably true. For decades, we've searched for radio signals, mechanical evidence, and structured messages. But what if meaning hides not in code, but in pattern, in the persistence of something that defies entropy? Every culture has equated order with intention. Maybe that instinct isn't superstition. Maybe it's recognition. Maybe symmetry is the language. 7 jets, 1 halo. A rhythm that ignores decay. A machine or a miracle, it didn't matter. It was coherent, surviving chaos. And in that coherence, something human awakened. People began to describe the event in spiritual terms. Not religion, but resonance. The sense that we had been briefly acknowledged by a universe that rarely looks back. Some called it humbling. Others called it terrifying. Both were right. Because humility and fear are twins, the mind reflects when faced with something vaster than comprehension. Late in December, as the object dimmed beyond visibility, a quiet grief settled over the community. The telescopes had gone blind to it, but its absence felt heavier than its presence ever had. It wasn't just that we had lost sight of a mystery. It was that the mystery had, for a moment, made us feel seen. Perhaps the real message of 3I, Atlas wasn't that we're being watched, but that we're finally capable of noticing. In the stillness that followed, the discourse turned inward. If meaning exists only where perception meets pattern, then maybe the universe doesn't need to send signals at all. Maybe awareness is already woven into its fabric. Every law, every symmetry, every improbable survival, an echo of consciousness diffused across matter. And perhaps that's why the object looked engineered, not because it was made by hand, but because creation itself has always been intelligent in ways we're only beginning to sense. A philosopher of science phrased it like this: we didn't discover a probe, we discovered a mirror, and the reflection looked back. That's the paradox at the heart of wonder. The more we search for the alien, the more the alien reveals our own outline. 3I. Atlas might be ancient technology, or it might be physics performing art. Either way, the effect is the same. For the first time in a long time, humanity stopped arguing long enough to share the same silence. And in that silence, something profound happened. We remembered what curiosity feels like before it becomes fear. The object is still out there, fading into darkness beyond Mars' orbit. We can no longer see it, but it remains in our equations, our memory, our questions. Maybe it never watched us in any literal sense. Maybe the watching was mutual, the universe observing itself through our astonishment. We've built the machines, now they're showing us things we can't explain. For centuries, astronomy was about light and patience, one pair of eyes, one night, one image at a time. But we don't look at the sky that way anymore. We've handed our sight to machines arrays that never blink, algorithms that never sleep. And in the faint afterglow of 3I, Atlas, those machines began seeing patterns that human eyes could never hold long enough to believe. The Vera C. Rubin Observatory in Chile had just begun its full-sky survey when the anomaly data came in. It was designed to capture everything, 30 terabytes of images every night, scanning the heavens in perfect rhythm, repeating, comparing, learning. Not a telescope, really, but a memory system for the universe. Its AI didn't just take pictures, it learned how to notice. So when 3I, Atlas, slipped into its field, the system logged something subtle but unprecedented. A repeating geometric signature embedded in the comas, brightness profile 2 ordered to be noise, too faint to classify. Human operators flagged it, unsure what to call it. The machine had already labelled it. Unknown persistent pattern, type 47. That was the beginning of a quiet revolution in observation. We had built instruments so powerful that they began discovering things we didn't yet have the language for. The AI wasn't biased by what was possible. It didn't know fear, pride, or institutional skepticism. It only knew contrast and continuity. Where a human saw blur, it saw recursion, fractal repetition in the jets, symmetrical pulsation in the brightness. It's behaving like an information system, one analyst murmured. Then maybe it is one, another replied. The statement wasn't recorded in any publication, but it spread through message threads like static. For the first time, it felt like the telescopes were trying to teach us something about our own limitations. We built machines to look further, but what they returned wasn't just distance, it was difference. They were showing us that the universe isn't a static picture. It's a living computation. 3I, Atlas wasn't the only anomaly the Rubin AI flagged that month. It found dozens of faint objects with slight, rhythmic irregularities, micro-fluctuations in luminosity that didn't match known orbital mechanics. Nothing as dramatic as 3I, Atlas, but enough to make one question whether the sky itself is full of signals too subtle for human intuition. At Caltech, an independent algorithm cross-checked the dataset. It didn't look for shape. It looked for behavior, how objects respond to light over time. And the result was uncanny. 3I. Atlas's light curve resembled that of a control system, a feedback loop adjusting for stability. In mechanical terms, it behaved like something maintaining equilibrium through self-correction. That realization hit hard, because self-correction is the threshold between reaction and intention. The paradox deepened. We had designed machines to see clearly. Now they were seeing too much. The telescopes could quantify, categorize, confirm, but not understand. Their clarity exposed the next wall. Comprehension. It wasn't the sky that was hiding its meaning, it was us, still bound by our need to reduce everything to the familiar. AI has no myth, one astrophysicist wrote. It just measures. And yet, it's the first to glimpse what might be meaning. The Rubin Observatory's logbook for those nights reads like poetry disguised as data. Every entry begins the same. Pattern detected. No excitement, no bias. Just pattern after pattern, cosmic rhythm, mathematical breath. And behind those numbers, a strange humility began to grow in the scientific community. Because for the first time, the tools we had created weren't confirming our expectations, they were transcending them. They were showing us that our notion of natural might be too small, our definition of intelligent too narrow. In a world overflowing with speculation, AI became the unexpected voice of restraint. It didn't say aliens. It didn't say artifact. It simply refused to classify. A human might call that indecision, but maybe it was wisdom. There's an irony here. The more intelligent our machines become, the more they remind us of the limits of intellect itself. Because pattern recognition doesn't equal comprehension. A telescope may see everything, but seeing is not the same as knowing. And perhaps that's the point. Perhaps the universe waits for us to rediscover humility through the eyes of our own creations. When the Rubin AI projected 3I Atlas trajectory forward, it generated a set of probabilities that no one expected. The most stable models didn't lead outward into the interstellar void. They curved gently toward the inner solar system, looping past Mars in early 2026 before fading. Was it a computational artifact? Maybe. But if it was correct, then the object wasn't escaping. It was a survey, the same way we were. Some began to see poetry in the symmetry. We built eyes to watch the stars. And now, through those eyes, the stars were watching back. Maybe intelligence doesn't travel across space, a researcher mused. Maybe it emerges simultaneously wherever curiosity becomes self-aware. That line made it into a TEDx talk later that year, though few recognized it as a whisper from this story. In many ways, the discovery of 3I, Atlas, marked the end of an era. Not because we solved the mystery, but because we learned that solving might not be the point. Our telescopes, our AI, our relentless classification, all of it had led us to the threshold of something bigger, the realization that explanation is not the same as connection. The machines had become extensions of our wonder, teaching us how to look without demanding certainty. When the Rubin AI's final nightly report was archived, it included one small note at the end, a human operator's edition, typed quietly after hours. We gave the universe eyes, and it looked back through them. No data, no equations, just that. And so, the era of human observation gave way to something shared, a vision between us and the instruments we built, both trying to interpret a cosmos that may be aware in ways we haven't yet learned to name. What if it's not saying any but, speaking without sound? For weeks, data teams argued over composition, orbit, acceleration, but in the background quietly, almost reverently, another conversation began. Not about what 3I, Atlas is, but what it might be doing. Because sometimes communication doesn't need language, it just needs rhythm. The jets had always been the focus, the 7 plumes forming a near-perfect symmetry, their pulses repeating with mechanical grace. At first, we called it coincidence, then stability. Now, some began calling it something else. Syntax. If you stripped away expectations, no words, no binary, no signal bursts, and looked only at time, brightness, and spacing, the structure resembled a code, a pattern emerging out of the void. Each jet flared with slight irregularity, like syllables in a phrase. The gaps weren't random, they followed ratios found in harmonic resonance, the same mathematics that defines musical scales, atomic spacing, and even the orbits of moons. Nature loves harmony, so does intelligence. A linguist from the SETI Institute was the first to say it aloud. If this were communication, we wouldn't understand the language. But we'd recognize the geometry. That statement changed the tone of every meeting. Suddenly, astronomers, mathematicians, and semioticians were speaking the same language numbers. because geometry doesn't lie, and silence, when patterned, becomes a message of its own. Through the Vera Rubin Observatory's archive data, analysts reconstructed the brightness curve across hundreds of frames. When plotted in 3D, the light peaks formed a wave that wasn't purely periodic. It oscillated with a nested structure, what mathematicians call quasi-harmonic modulation. Translated to audio, it didn't sound like noise. It sounded like a heartbeat fading into breath. "It's not transmitting," one observer whispered. "It's resonating." The idea spread like wildfire, but not in headlines behind closed doors, in encrypted channels, late-night calls between labs. No one wanted to claim message, but everyone felt it, because the pattern was too patient, too measured. A comet erupts and dies. A probe reacts and moves. 3I, Atlas, did neither. It composed. Every fluctuation, every pulse of brightness seemed to follow a recursive ratio 7:1, 1:7, repeating, like a mirror folding into itself. If you plotted it as geometry, the map resembled an ancient symbol circles nested inside circles, a pattern that echoed through sacred art and modern physics alike. Coincidence? Perhaps. But a beautiful one. When the data was presented at a private symposium in Geneva, someone asked the question that silenced the room. If this is a message, who or what is it for? Because the object wasn't broadcasting radio waves or directed beams. Its only medium was light reflected from the sun, modulated by motion and plasma. That means the message, if it exists, is passive, not sent, but written, like a note left on the edge of time, waiting for anyone with eyes to read it. The concept resonated with everyone who had watched the mystery unfold. Perhaps the object wasn't trying to speak at all. Perhaps it was demonstrating something simpler, that silence can carry structure. That meaning doesn't need translation, it only needs recognition. To speak without words, one scientist wrote, is to trust that awareness will find you. Across cultures, silence has always been a form of reverence. Monks, physicists, poets, they all touch it differently, but it carries the same current, truth too large for speech. 3. I, Atlas, embodied that silence, not emptiness, but fullness, density of meaning so compact it could only be felt, not decoded. As it drifted away from the sun, the jets dimmed but stayed aligned. The geometry persisted long after the brightness faded, as if written into the dust itself. Some called it the language of stillness. Others called it proof of presence. Either way, the effect was the same. Wonder returned to science. In the wake of that realization, teams around the world began reanalyzing old Comet data, asking whether similar patterns in the silence had been missed before. Most found nothing. But a few faint echoes appeared, small, structured anomalies buried in decades-old archives. If those hold, it means 3I, Atlas wasn't alone. It was part of a lineage. The conversation stretched across cosmic time. Late one night, a young astronomer at the Rubin Observatory decided to superimpose all the light curves of 3I, Atlas, aligning them not by time, but by intensity phase. The result looked like interference waves overlapping, cancelling, and reinforcing. When she enhanced contrast, a faint image emerged in the pattern. 7 points spiraling around one centre, repeating infinitely smaller each time. Fractal, recursive, not random. The universe speaking in its oldest dialect. Geometry. By now, 3I, Atlas, had passed beyond telescope range. But the idea it left behind was harder to lose. What if every physical law is already a language? What if communication doesn't require intention-only pattern? Perhaps 3I, Atlas wasn't built to deliver a message. Perhaps it is the message. In that light, silence stops being absence. It becomes an invitation. A call to slow down enough to notice what's already being said between stars, between atoms, between breaths. And maybe that's what 3I, Atlas, was teaching us all along. The universe doesn't shout, it hums. Some messages aren't meant to be decoded, just witnessed. By the time 3I, Atlas slipped past Mars' orbit, its light was faint, barely a whisper against the solar wind. The data had slowed to a trickle, the jets were dim, the symmetry fading into shadow. But something in our way of seeing had changed. For the first time in decades, Science wasn't straining to prove or disprove. It was learning to listen. The idea came from plasma physicists studying the solar magnetic field. They noticed that 3I, Atlas, behaved differently from any known comet under magnetic stress. Normally, when the sun's field lines encounter a plasma tail, they drape wrapping around the coma like wind bending around a mountain. This effect distorts the shape unpredictably. But 3I, Atlas didn't distort. Its jets curved in synchrony with the field, flowing as if anticipating the solar current, rather than reacting to it. The physics suggested feedback a dance, not a collision. At Johns Hopkins Applied Physics Lab, analysts ran magnetohydrodynamic simulations using the data from Parker Solar Probe and SOHO. When they modeled a passive comet, the tail scattered chaotically. But when they introduced a parameter that allowed for magnetic awareness, a built-in alignment tendency, the pattern matched the observations exactly. It's almost like the object is tuned to the field, the lead researcher said. That word tuned shifted everything, because it implied not dominance but harmony, not a force fighting the solar wind, but one flowing with it. Maybe that's what listening really means in cosmic terms. Not waiting for a signal, but attuning to the hum that's already there. The universe doesn't broadcast to us in words or frequencies we can easily parse. It speaks through interaction, through the shape of movement, the grace of adaptation, and perhaps 3I, Atlas, was never speaking in the way we imagined. Perhaps it was showing a demonstration of how awareness behaves when it stops resisting its environment. The plasma readings from Parker confirmed a fascinating speaking its eye detail. Each time the sun released a minor flare, the object's velocity changed fractionally, never in defiance, always in resonance. It absorbed impact like an instrument adjusting pitch. That's when someone in the lab made a quiet analogy. If you strike a tuning fork beside another tuned to the same note, the second begins to vibrate. Maybe this is the universe's version of that. The statement was half poetry, half physics, but no one disagreed. In earlier centuries, we called that kind of thinking mystical. Now, with data to back it, it looked like a new kind of science, receptive science, not about conquering mystery, but allowing mystery to teach by example. We used to believe understanding required dissection, equations, and naming. But 3I, Atlas, reminded us that comprehension can also come from stillness. Just watch, just listen, just be quiet enough for patterns to reveal themselves without force. Even as the data faded, the world's telescopes continued tracking the magnetic afterglow. The subtle ripples, 3I, Atlas, left behind in the solar field. Like fingerprints in plasma, they lasted for weeks, a faint spiral of charged particles twisting gracefully along the field lines, holding formation long after the object was gone. Those ripples told a story not of propulsion or engines, but of relationship. Because in magnetism, shape is conversion. Every curve is a reply. If you map those curves, they form something eerily familiar. The shape of a helix, the same geometry encoded in DNA, in shells, in galaxies. Nature repeating itself across scale, as if reminding us that harmony is the default language of existence. What if the message of 3I, Atlas, wasn't technological at all? What if it were biological in spirit, showing us that intelligence doesn't always need consciousness, that resonance can look like thought? To align with a field, one physicist wrote, is to acknowledge it exists. Maybe that acknowledgement is the first step in communication. By January, observation reports began to slow. The object was fading beyond the reach of visible light. But what lingered wasn't disappointment, it was serenity. Because, somehow, we had already learned what we needed to. 3I, Atlas had taught, by example, not instruction. It demonstrated that there's more to knowledge than analysis, that awareness can be participatory, not possessive, that science, at its best, is an act of empathy toward the unknown. The journalist asked one of the mission scientists what he thought the object really was. He paused, then answered softly, "It doesn't matter. What matters is that it made us listen differently." That statement became the headline misinterpreted by many, but quietly understood by those who had watched this journey unfold. Because the point was never to find an answer, it was to rediscover the ability to hear the cosmos without forcing it to fit our vocabulary. In the final review paper of the year, one footnote stood out among the dense equations and data tables. Observed stability. consistent with resonance-driven adaptation. A small phrase, easily overlooked, but for those who'd followed every photon, it was a revelation. It meant we were finally willing to describe the unknown not as error, but as participation. That's what listening with different ears really is, not expecting to decode a secret, but realizing the universe never stopped speaking. We were just too loud to hear. And as 3I, Atlas drifted into darkness, silence reclaimed its space not as emptiness, but as awareness. Every sensor, every scientist, every machine that once strained to catch its light now waited in quiet alignment, like an orchestra between notes. Because once you learn to hear the rhythm behind the noise, you start recognizing it everywhere, in solar wind, in heartbeats, in the pulse between atoms, the same geometry, the same cadence, the same invitation. Some messages aren't meant to be decoded, just witnessed. It's fading now. We may never get another look. After months of light, motion, and theory, the sky returned to silence. The object that had filled our nights with questions was retreating into the cold. Its brightness fell below magnitude 18, too dim for even Rubin's wide-field eye to track with certainty. Every observation now felt like a goodbye written in photons. In the final weeks of visibility, observatories around the world coordinated one last campaign, a synchronized attempt to capture 3I Atlas before it vanished completely. From Chile to the Canary Islands, telescopes swept the same coordinates in shifts, chasing a fading trace of light through the noise. It wasn't about discovery anymore. It was about keeping it visible for as long as possible, as if attention itself could hold it in place. Every exposure feels like breathing into the dark, one astronomer wrote in her log. The object was already outbound, climbing beyond the plane of the ecliptic, heading for a region of sky too faint for human eyes and too distant for our machines. It was slipping from us not with spectacle, but with grace. The last clear detection came on a windless night in Namibia. The image looked almost empty, one faint pixel of light buried in background noise, but zoomed in, that single point was unmistakable. The same hue, the same subtle pulse that had carried us through months of wonder. And then, by morning, it was gone. Not destroyed, not exploded, just beyond reach. The silence that followed wasn't shock, it was ache. All around the world, data centers began shutting down their live feeds, archiving terabytes of images and telemetry. Each file is labeled, time-stamped, and secured. Every number is a fragment of a memory that was already drifting into legend. Scientists are trained to let go, to move from one mystery to the next, but this one resisted closure. "We watched something impossible," one wrote, "and now it's gone, and I'm not sure what that makes us." In the official logs, the final orbital parameters were precise but hollow. Outbound trajectory, 38 degrees above the ecliptic, eccentricity, 6.14, hyperbolic excess velocity, 61.2 kilometers, clean numbers, lifeless truths. But between those decimals lay the ache of something more human, an unspoken recognition that we had witnessed a moment we might never experience again, because 3I, Atlas, wasn't just leaving the system, it was leaving us. Even as it faded, the data still spoke softly through analysis. A faint plasma trail, detected by Parker's solar probe, weeks after optical contact was lost, hinted that the object's structure remained intact. No fragmentation, no debris. It hadn't broken apart. It had simply continued whole, deliberate, silent. That detail carried both comfort and sorrow. Comfort, because it meant the story wasn't ending. Sorrow, because it would unfold somewhere we could no longer follow. The European Southern Observatory released one last image, a long-exposure composite of its outbound path. The frame showed a faint arc crossing a star field, ending abruptly at the edge of detection. The caption read, "Final confirmed trace of 3I, Atlas, December 29, 2025. But that line felt incomplete, because there is no final when what you're chasing never truly stops. In press conferences, scientists tried to sound composed. "We've learned a great deal," they said. "This will inform future models." But the tone was subdued, almost elegiac. They knew they hadn't solved it. They had only shared in its passing. In online forums, amateur astronomers posted blurred images and quiet goodbyes. Some used poetry, others numbers. One simply wrote, "Thank you for showing us that not everything needs to explode to be extraordinary." As 3I, Atlas receded into darkness. It left behind something intangible, the awareness that observation has a cost. Every discovery is also a farewell. To see clearly is to watch something vanish. To understand is to let it go. There was one last attempt, a coordinated radar sweep from Goldstone, Arecibo's successor array, and ESA's tracking network. The result was inconclusive. One faint echo, possibly interference, possibly real. If it was real, it meant the object had briefly slowed again, just for a moment, as if turning its gaze backward. But that could have been imagination. Scientists dismissed it as statistical noise. Still, many quietly chose to believe, because it's easier to mourn something that looked back. The world moved on, but the silence it left behind wasn't empty. It hummed, faintly, with continuity like the tail end of a song still echoing long after the singer has left the stage. Even now, deep space networks occasionally scan its predicted route, hoping for a flicker, a signal, a glint, a mistake in our models that would mean it isn't gone entirely. None has found anything, and yet, each year, the telescopes look again. Hope, it seems, has orbital momentum. In the absence of data, myth rushes in. Some call it a messenger, others call it a mirror. A few believe it was never meant to stay, that its purpose was to pass through, to remind us that the act of watching changes both watcher and watched. Perhaps that's why it left so quietly. It had already done what it came to do. Sometimes, the most eloquent message is departure itself. We may never know where it's going, or whether it will ever encounter another star, another set of curious eyes. But in the story of human curiosity, 3I, Atlas has already completed its orbit not around the Sun, but around our imagination. It entered as data, it left as meaning, and somewhere between those 2 points, it became something sacred. What if the structure is real and repeatable? The light was gone, but the dust remained. Even as 3I, Atlas faded beyond the reach of telescopes, the sun's own light kept tracing its path, a faint shimmer of reflection, a signature written across the void. And in that residue, hidden between photons and patience, was a map. A map not of direction, but of design. The first to notice were not astronomers, but data archivists reviewing scattered photometry. When they overlaid hundreds of long-exposure images taken during its closest approach, something unexpected emerged. The residual dust trail didn't scatter randomly. It formed a lattice, subtle, but geometric, like threads drawn by an invisible hand. Each arc of material curved at consistent angles from the object's former axis of rotation, suggesting not chaotic venting, but precision, as if the ejected dust had followed a planar symmetry aligned to a hidden framework. "It looks like architecture," one analyst whispered. To test it, researchers reconstructed the trajectory frame by frame, compensating for the sun's gravitational and magnetic effects. The result was astonishing. 7 main trails, matching the original jet directions almost perfectly, radiating outward like spokes of a wheel. Even more puzzling, those lines weren't random in time. They appeared in repeating intervals, each layer offset by rotation, forming a spiral projection in 3 dimensions. If the object were spinning and releasing material from symmetrical vents, this pattern would appear naturally. But if that were the case, the spiral should deform as solar pressure acted unevenly. It didn't. The pattern held its proportions even as it drifted outward. It wasn't chaos. It was choreography. Some called it the symmetry model. Others, more poetically, the map written in dust. The model's premise was simple. By studying the shape of what remained, we could infer the structure of what created it. Every jet, every plume, every curve of dust was a line of handwriting, a cosmic script written in persistence. And together, those lines told a story not of destruction, but of memory. At the University of Helsinki, a research group ran simulations using particle projection software. They assumed a nucleus rotating with a period of 5.9 hours, releasing dust through 7 vents equally spaced along its equator. The outcome? A near-perfect match to the real observations. Even the subtle curvature, the faint, Almost artistic bending of the outer trails was consistent with a body precessing slightly around its spin axis. Only one variable refused to fit: the axis tilt. To match the observed pattern, the spin axis had to be oriented within 5 degrees of the ecliptic, aligned not randomly but precisely parallel to the sun's equator. That's not where nature usually points its compass. It's where navigation does. If that alignment was a coincidence, it was an improbable one. If it wasn't, it meant something had guided the geometry, whether magnetic, gravitational, or intentional. The dust map became a new kind of Rosetta Stone, an artifact we could study long after the object itself had disappeared. Even silence leaves structure behind. The model revealed something else. When the 7 plumes intersected at projected distances, they formed repeating nodes, points of reinforcement where the density of particles increased sharply. In physics, those nodes looked like interference patterns. In human language, they looked like a design. Some speculated the pattern could be a byproduct of synchronized venting, a kind of natural gyroscopic stabilization. Others dared a more radical thought: maybe the pattern was meant to be seen. If the geometry held under multiple rotations, it could have been visible from any system. The object passed an ongoing demonstration of balance, written in light and dust, a message not in code, but in structure. That idea rekindled fascination worldwide. Researchers who had already moved on returned to their datasets. AI programs began scanning historical comet archives, searching for matching geometries, and, astonishingly, they found a few candidates. Comets from decades past, long dismissed as unremarkable, showed faint echoes of the same 7-fold symmetry. Not identical, but suggestive. Like distant dialects of a shared language. If verified, it would mean the pattern was repeatable, either a recurring natural template or a recurring design philosophy. Neither answer was ordinary. Meanwhile, plasma physicists noticed something else in the residual data: faint traces of ionized nickel along specific dust lanes, but not others. It was as though certain jets had been chemically distinct, some releasing ordinary carbon compounds, others releasing metallic grains. Why the differentiation? If the goal was simple venting, uniform composition would make more sense. Selective release implied control. It implied intent. Even its debris knows what to do, one researcher joked. But no one laughed for long. The more scientists tried to reduce the symmetry to physics, the more symbolic it began to feel. Not mystical, just too elegantly consistent to ignore. What if the universe, in its endless cycles of collapse and creation, leaves behind repeating fingerprints of intelligence? Not conscious, perhaps, but formative. Patterns that build themselves. Structures that remember how to stay beautiful, even when their builders are gone. 3. I, Atlas, had left such a fingerprint, traced in dust fine enough to drift for centuries, a record of symmetry durable enough to outlast meaning. By February, the trails had stretched into thin threads of particulate mist, invisible to the naked eye, but still traceable through polarization maps. The pattern persisted fragile, ghost-like, but still there. It was as if the universe itself refused to erase it. In those faint threads, we found reassurance that even in departure, something remains ordered, that chaos, when patient enough, writes poetry, and that sometimes the most honest evidence of existence isn't the object itself, but the geometry it leaves behind. As one astronomer wrote in her closing report, "We may never know what 3I, Atlas was, but we know what it understood, how to draw meaning into dust and let the light read it. The sun can curve dust like rivers bend light." That's what the simulations began to reveal, a dance not of chaos, but of current. For decades, we've imagined the solar wind as a simple storm, charged particles streaming outward, scattering everything in their path. But the closer we looked, the more it resembled a river system, fluid, structured, sensitive to every curve of the magnetic field. And when 3I, Atlas, passed through that river, something remarkable happened. The current changed course. It began with a set of readings from the Parker Solar Probe, orbiting just 0.05 AU from the Sun during the object's perihelion window. The instruments registered a faint but distinct magnetic shear, a bending of the interplanetary field lines not explained by solar flares or coronal mass ejections. At first, it looked like background noise. But when analysts overlaid the timing with 3I Atlas's trajectory, the correlation was perfect. The magnetic field hadn't bent randomly. It had curved around the object like plasma flowing around a stone in water. Only one problem. 3I Atlas was too small to do that. Its nucleus, even at generous estimates, was less than 2 kilometers across, far too small to deflect a magnetic field line measurable at millions of kilometers scale. So the question arose, how could something that small reshape the solar wind itself? The answer came slowly, from physics no one had expected to use. The Lorentz force, the interaction between moving charged particles and magnetic fields, governs the behavior of plasma dust. Normally, comet dust is electrically neutral, but near the sun, intense radiation can charge those grains, turning them into tiny conductors. When 3I Atlas released its dust, those grains weren't inert. They became charged particles embedded in a magnetic flow. And when a charged stream interacts coherently with magnetic fields, it doesn't scatter, it conducts. Think of it like a bow wave, one physicist explained. Except this wave carries current. Under ordinary conditions, that effect would be chaotic dust grains, interacting randomly, producing noise. But the structure of 3I Atlas wasn't ordinary. Its symmetrical jet array released material in balanced, repeating bursts, producing an even charge distribution. That regularity acted like tuning, organizing the plasma, allowing it to shape the solar wind instead of being consumed by it. The sun's field responded accordingly, bending smoothly, gently as if guided by invisible hands. The Parker probe's magnetometers recorded the distortion clearly. In one 48-hour window, the magnetic field angle deviated by 4.7 degrees, not enough to disrupt the heliospheric flow, but far too coordinated to be random. Particles accelerated along that curvature, then relaxed back into equilibrium once the object had passed. The data showed harmony, not resistance. Interaction, not interference. The object didn't fight the solar wind, one analyst wrote. It collaborated. That single phrase opened a new realm of inquiry, one that blurred the line between observation and philosophy. Because what if that collaboration wasn't a coincidence, but a capability? Theorists proposed a radical concept, plasma steering. If the object's surface was conductive or coated in magnetic material, it could, in theory, manipulate charged dust using induced fields. In simpler terms, it might not just survive the solar wind, it might use it. This would explain nearly everything. The sunward jets, the stable symmetry, the non-gravitational acceleration, the absence of exhaust. In one model, the 7 jets acted as electromagnetic nozzles, each releasing ionized dust in precise phase with solar wind oscillations, generating a small but continuous thrust. No fire, no fuel, just resonance. At the Max Planck Institute for Solar System Research, a small team tested this theory with high-fidelity plasma modeling. They simulated a nucleus carrying a weak magnetic dipole barely measurable, but enough to anchor a plasma sheath. When charged dust was ejected rhythmically, it interacted with solar wind in repeating cycles, forming stable corridors of flow, miniature magnetic rivers curving outward from the nucleus. The results matched the observed data within 3% error. That's practically a confession. We've been thinking of the sun as the sculptor, the lead physicist said. But what if this object was sculpting the sun too? For the scientific community, the revelation was intoxicating. For the human mind, it was humbling. We'd always imagined exploration as a force, rockets, engines, propulsion. But here was something ancient or advanced, moving through plasma by cooperation. It didn't conquer the wind, it listened to it. It shaped motion the way a musician shapes tone. NASA's Heliophysics division quietly noted the implications. If plasma steering is real, it could revolutionize our own future missions. Imagine a spacecraft that navigates magnetic currents like sailboats, powered not by engines but by alignment. The same principle that shaped 3I, Atlas could, someday, carry us to other stars. The idea was so radical that some engineers began referring to it half-jokingly as magnetic sailing. But no one was laughing by the time Parker's next transmission confirmed yet another field deflection, weeks after the object had already departed. Something in the solar wind was still, remembering it. In a way, 3I, Atlas had left behind an invisible trail, not of dust, but of curvature. Subtle arcs in plasma density, like fingerprints imprinted on the magnetic field itself. When mapped, they resembled a spiral expanding outward from the sun, a continuation of the geometry first traced in dust. The same symmetry, the same rhythm, only now written in plasma instead of light. To scientists, it was data. To poets, it was proof that even the smallest traveler can leave music in its wake. Because what the sun does to dust isn't destruction, it's translation. Heat becomes motion, motion becomes form, form becomes echo, and sometimes that echo lingers long enough for us to read it. In the end, the story of 3I, Atlas, and its dance with the solar wind became less about mystery and more about kinship. We discovered that plasma, dust, and light are not separate languages. They're dialects of the same universal conversation, and if the universe can curve its own currents into harmony, maybe intelligence was never an exception. Maybe it was always the rule. The sun curves dust, dust remembers shape, and we by watching complete the circle. The further we look, the stranger we become. Every age, the flatty of discovery, begins with instruments and ends with a mirror. After 3I, Atlas, astronomy found itself staring into one. We built telescopes to see the universe more clearly, but clarity has a cost. Each layer of resolution strips away comfort. Every anomaly challenges the mind that found it. And somewhere along that path, the frontier stops being out there. It starts being us. By early 2026, as the object vanished into darkness, its aftershock settled into the institutions that studied it. Labs, observatories, and universities quietly confronted an unspoken truth. Our tools had outgrown our certainty. The data was flawless. The math is consistent. The mystery remained. 3I, Atlas, had behaved like a probe, a plasma sail, a sculpture of physics, and yet none of those identities were provable. The real anomaly wasn't the object. It was our inability to agree on what it meant. Among scientists, that state of tension has a name: anomaly fatigue, the slow exhaustion that comes from staring too long into the unexplained, because it's not easy to live with unclosed parentheses. The human mind aches for closure. It wants the cosmos to rhyme. But the universe doesn't rhyme, it resonates. In the months after the final observation, a shift occurred in scientific culture, a quiet redefinition of purpose. Where once the goal had been explanation, now it became endurance. How long can we sit with what we don't know before rushing to fill the silence? Every mystery has a half-life, one astrophysicist admitted. The longer it lives, the more it tells us who we are. That realization didn't appear in a press release. It appeared in small things: the tone of published papers, the gentler phrasing of conclusions, the rise of a single recurring word in the scientific lexicon: uncertain. In science, uncertainty is honesty, but in the human psyche, it's unease. We were learning to hold both. Historians will likely call this period the post-Atlas turn, the moment the pursuit of knowledge began to include self-awareness as a variable. Because for the first time, researchers began asking not only what the data said, but why we needed it to say anything at all. Observer bias, long discussed as an academic concept, has now become deeply personal. Were we finding intelligence or inventing it? Were we discovering symmetry or projecting our own craving for order onto the void? Maybe the object isn't strange, one physicist said. Maybe it's us. Finally seeing our own reflection without filters. In seminar halls, conversations turned almost philosophical. Is it possible to study the universe without changing it, without our attention shaping the pattern we think we're observing? Quantum mechanics had whispered that truth a century ago. 3I, Atlas, had made it intimate, because if even dust can remember symmetry, what does that say about the observer? Meanwhile, in data archives, a different kind of evolution was happening. Young scientists began labeling their projects not as searches but as listenings. It was subtle but revolutionary, because listening implies respect for what's beyond control. It acknowledges that understanding might not come through dissection, but through patience. A culture raised on conquest, on decoding, naming, and owning was learning to stand still. Some resisted. "There's nothing mystical here," one senior researcher declared at a conference. "It's physics, not philosophy." But even he couldn't deny the change in atmosphere, the pause before every conclusion, the careful phrasing of every certainty. Humility had returned to science, not as surrender, but as precision. Because arrogance clouds data, humility clarifies it. In the quiet that followed 3I, Atlas, a new generation of thinkers emerged, scientists comfortable at the boundary between reason and reverence. They didn't reject logic, they expanded it. They treated wonder not as weakness, but as evidence that curiosity was still alive. And that curiosity, more than any instrument, became the threshold of discovery. At a memorial symposium for the event, yes, a memorial, the keynote speaker said something that lingered. 3I, Atlas didn't bend the laws of physics. It bent the culture that studies them. The audience fell silent, because everyone knew it was true. The culture of science had long idolized certainty, but in the wake of 3I, Atlas, certainty felt fragile, too small to hold the vastness it had revealed. What replaced it wasn't despair, but something gentler, intellectual humility, not ignorance, not defeat, just awareness that knowledge, no matter how vast, will always be smaller than wonder. And that's not a flaw, that's the invitation. In private journals, researchers wrote differently now, less like engineers, more like poets trying to describe light they can't quite touch. Even the data tables carried a new kind of tenderness notes, acknowledging what couldn't be measured. Possible plasma resonance, potential field memory, unknown but beautiful. Those three words, unknown but beautiful, became the quiet motto of a field reborn. In the end, maybe that's what 3I, Atlas, really changed. Not our understanding of the universe, but our willingness to meet it halfway. Because the further we look, the more we see ourselves in what we find our longing, our limitations, our reflection in the patterns of dust and plasma. And if the object taught us anything, it's that knowledge is not the opposite of mystery. It's the continuation of it. Every time we reach for the edge of understanding, we also reach the edge of ourselves. That edge, that trembling boundary between reason and awe, is the human threshold. And maybe, just maybe, that's where we were always meant to stand. It didn't hide. We just hadn't quite quieted down yet. For centuries, humanity spoke of the universe as if it were withholding its secrets, a silent keeper of mysteries, teasing us with fragments of truth. But what if the silence was never secrecy? What if it was an invitation? When the light of 3I, Atlas, finally vanished beyond reach, something remarkable happened. The debate slowed. The models stopped multiplying. For the first time since the discovery began, there was nothing left to analyze, only to feel. And in that stillness, something shifted. We realized the universe hadn't gone anywhere. It was we who had been too loud to hear it. For centuries, knowledge has been an act of conquest. We chased understanding like hunters chase prey through equations, through telescopes, through noise. But noise doesn't reveal truth. It drowns it. And as 3I, Atlas drifted into darkness, we were forced into the one-state science rarely allows silence. No more data, no more control, just awareness. It felt like a loss, but in that absence, something new appeared. Presence. Astronomers described it in small, private ways. One said it was like a room finally emptied of machines where you can suddenly hear your own breath. Another compared it to the moment between lightning and thunder, suspended time, pure attention. It was the same silence 3I, Atlas, had carried all along, only now we were finally quiet enough to notice. The universe was never withholding, one physicist wrote. We were just interrupting. What followed wasn't discovery in the usual sense. It was acceptance, the kind that doesn't feel like surrender, but like alignment. Because uncertainty, once feared, had become a kind of grace. Every unanswered question, every anomaly we couldn't tame, felt less like failure and more like permission to wonder again. We had built machines to measure the cosmos, but the most profound measurement turned out to be internal, the distance between noise and stillness. Across observatories, something subtle changed. The language of research proposals grew softer, less about conquest, more about communion. Instead of detect, they wrote listen. Instead of prove, they wrote explore. The vocabulary of control was giving way to the vocabulary of participation. Science, one researcher said, is not about forcing answers, it's about learning to deserve them. And perhaps that's what 3I, Atlas, was meant to remind us. That the universe doesn't need to hide because truth isn't a secret, it's a frequency. And the moment we stop shouting our questions, the answers begin to resonate on their own. The observer effect, so often confined to quantum theory, had finally expanded into philosophy. We began to see how attention itself changes what is seen not through magic, but through intimacy. Every observation carries a kind of energy, a focus that shapes interpretation. And so, the silence after 3I, Atlas wasn't absence, it was reflection. The cosmos was simply waiting for us to look without demanding. In that realization, cosmic humility returned not as despair, but as peace. Because if the universe is vast enough to hold both chaos and meaning, then we no longer have to force one to defeat the other. They coexist, like night and dawn sharing a single horizon. Maybe that's why 3I, Atlas, came when it did, to remind us that even confusion can be holy if you approach it gently enough. The old myths spoke of gods hiding wisdom in stars, so that only the worthy would find it. But maybe worthiness was never about intelligence. Maybe it was about patience, the willingness to listen without expectation. That's what the ancients called reverence. We just call it data collection. Months later, when the solar wind readings finally stabilized and no trace of the object remained, Parker's solar probe transmitted one last dataset from the region. Nothing extraordinary, just ordinary plasma, quiet and calm. But when researchers plotted the field oscillations, they found something haunting, a faint harmonic resonance still lingering, as though the solar wind itself remembered being touched. The amplitude was too low for significance, but the pattern, it was beautiful. The silence still has structure, one analyst wrote. That phrase became a kind of closing line for the entire phenomenon, a recognition that not all echoes need to be understood. Some are meant to be felt. Maybe that's the final truth. The universe never hides. It simply speaks on a wavelength most of us forgot how to hear. The stars don't whisper answers, they hum continuity. Every orbit, every particle, every symmetry we chase, it's all the same song, patiently waiting for its listeners to stop tuning it out. In the end, 3I, Atlas didn't just redefine our idea of intelligence. It redefined our idea of a relationship. Because if the cosmos is aware, even just in pattern, in rhythm and law, then to study it is to engage in dialogue. And dialogue requires silence between sentences. Perhaps that's what we are to the universe, a pause long enough for it to hear itself think. When future generations look back at this era, they'll find the data, the equations, the debates, but they might also find something quieter, the first moment in modern science where silence became part of the method. It didn't hide. It never does. It only waited for us to calm down so the language beneath light could be heard again. Maybe we're not being watched. Maybe we're overhearing something. For decades, humanity's search for meaning in the cosmos carried a quiet arrogance. We assumed we were part of the conversation, that if messages existed, they were meant for us. But what if 3I, Atlas, didn't come to deliver anything? What if it simply passed through, and we, by coincidence, were standing close enough to hear the echo? The shift began with a small insight buried deep in a technical report from the SETI Institute. Analyzing radio background during 3I Atlas's passage, the team detected faint modulations in the galactic noise, subtle oscillations too structured to be random, too faint to be localized. At first, they thought the signal originated from the object, but when they traced the source, it wasn't coming from 3I, Atlas at all. It was coming from everywhere, a diffuse hum, ancient and omnipresent, like static carrying the murmur of stars. The realization landed like a quiet thunderclap. We weren't the audience. We were inside the broadcast. That discovery reframed everything. Because maybe the cosmos doesn't communicate through directed messages or intentional contact. Maybe it resonates an ocean of overlapping transmissions so vast that each world hears only fragments of the whole. We had been scanning the sky like eavesdroppers on an infinite conversation, catching sentences without context, mistaking whispers for invitation. And perhaps 3i, Atlas, was simply one of the louder syllables, a bright syllable in a language the galaxy has been speaking since before we learned to listen. The concept spread quickly, Earth as listener, not target. It was humbling, almost comforting, because it removed both the pressure and the fear of being seen. We weren't special participants. We were bystanders blessed with sensitivity. The universe didn't single us out, it just didn't bother to hide. We're not in the message, one astrophysicist said. We're in the medium. Think of it this way. If the galaxy is a sea of resonant frequencies, magnetic, gravitational, radiative, then every object that moves through it leaves ripples. Planets, comets, stars, all whispering by motion alone. 3i, Atlas, was just one such ripple, its passage amplifying a signal that was already there. The fact that we noticed at all was the miracle. For the first time in the search for extraterrestrial intelligence, humility replaced expectation. SETI stopped asking, "Who's talking to us?" and began asking, "What are we accidentally overhearing?" It changed the science completely. Instead of hunting narrow-band beacons, researchers began studying galactic noise. The soft, persistent background hum of the Milky Way. Within that noise, patterns emerged. Harmonics, pulsations, rhythms, not entirely random. It was as if the cosmos were alive with unconscious communication, like neurons in a vast, dreaming brain. Maybe it's not intelligence sending signals, a researcher mused. Maybe intelligence is what happens when signals overlap. This realization also reframed the mystery of the signal horizon, that invisible boundary beyond which we can no longer distinguish one source from another. We used to treat intelligence, as a wall, a limit to understanding. Now, it looked more like a symphony, countless overlapping notes, merging into one continuous sound. If you listen to enough instruments at once, individual melodies disappear, but the harmony remains. Perhaps that harmony is consciousness on a cosmic scale. It was an idea both beautiful and terrifying. We are immersed in meaning, yet incapable of isolating its source. Our role is not to decode, but to attend to tune ourselves to the frequencies already vibrating through everything. That's what 3i, Atlas, had done, traveling not against the current, but with it, resonating as it went. It didn't create a signal, it revealed a signal. On Earth, this realization softened the existential tension that had haunted modern science. For decades, we had oscillated between two fears, that we were alone or that we were not. But now, a third truth emerged. We were never alone because we were never separate. Isolation was an illusion born of noise. Silence was never empty. It was filled with everything. In that light, even our instruments became part of the message. Every telescope, every radio dish, every listening array, they weren't eavesdropping tools. They were extensions of the same field, new ears grown by the planet itself. Earth had become aware of its own participation in the cosmic hum. We are not receivers, wrote one philosopher of science. We are resonators. This reframing changed more than astronomy. It changed how people saw themselves. In classrooms, teachers began describing science as learning to listen without interrupting. In documentaries, narrators spoke less about discovering aliens and more about understanding context. Even spirituality shifted. Prayers and signals, meditation and measurement, we began to sound like the same gesture, the act of aligning attention with something vast and continuous. The universe had always been speaking. We had simply mistaken its patience for silence. When the next wave of telescope data arrived quiet, clean, filled with faint structured noise, scientists didn't rush to explain it. They just listened, and for the first time, the act of listening felt complete on its own. Because maybe comprehension isn't the goal, maybe awareness is enough. The truth of 3i, Atlas, may never be written in a paper or proven by experiment, but its legacy will. Live wherever humans learn to pause before assuming meaning belongs to them. Maybe that's what the object gave us, not answers, but perspective. A reminder that humility and attention are the same skill at different scales, and if we can master them both, then the next time the cosmos murmurs, we won't mistake the echo for a summons. Well, simply listen, grateful to be within range. It wasn't a message, but it meant something. 3I. Atlas is gone now, beyond the pull of our instruments, beyond the reach of reflected light. Its orbit will never bring it back, yet somehow it doesn't feel finished. Because the silence it left behind doesn't close the story, it opens it. Weeks after the last observation, as telescopes turned elsewhere, a faint sense of anticipation settled over the community. Nobody said it aloud, but everyone felt it, that this wasn't the end. Something about the rhythm of events, arrival, revelation, departure, felt cyclical, like a breath paused between inhalation and release. And every breath has another that follows. The Parker Solar Probe, still orbiting the Sun in its looping descent, continued sending back plasma data. Amid the ordinary fluctuations, one sequence stood out, a subtle oscillation matching the same frequency once seen during 3I, Atlas's passage. Weak, persistent, repeating every 6 days. It wasn't confirmation of anything, but it was enough to remind us that echoes travel farther than their sources. Maybe the universe doesn't send messages at all. Maybe it leaves rhythms, patterns, waiting for whoever's quiet enough to notice the next one. And so, the search continued, but differently now. Not with expectation, but with awareness. Astronomers no longer hunted for spectacle. They looked for familiar, quiet, that same signature of order at the edge of noise. They didn't find another 3I, Atlas at least, not yet. But in the data from distant observatories, a few anomalies whispered through the static objects whose paths were slightly off, whose brightness curved against prediction. None conclusive. All intriguing, like faint footfalls in the sand, too far apart to form a trail yet close enough to make you wonder if someone else once walked here, too. Philosophers began calling it the Atlas effect, the transformation that happens not when you find answers, but when you realize the search itself is sacred. Because discovery isn't about possession. It's about participation. Every question expands the universe a little more by proving it can still surprise us. That's the real legacy of 3I, Atlas. It reminded us that curiosity is communion. Somewhere in the darkness between stars, the object continues, not tumbling, not broken, but steady, carrying its silent geometry through a sea of radiation and dust. It will outlast the sun, our species, perhaps even the Earth itself. And maybe, one day, another civilization will detect its trace, a small symmetrical pattern gliding through their sky. They'll wonder, just as we did, whether it's a rock or a messenger, a natural rhythm or a deliberate sign. They'll argue, they'll measure, they'll feel the same awe we felt, the same doubt, the same aching beauty of not knowing. In that moment, the conversation will continue, unbroken, because that's what the cosmos is, not a chain of answers, but an unending exchange between question and wonder. Every generation inherits the echo of the last and adds its own frequency to the harmony. Stars die, new ones form. Objects like 3I, Atlas drift between them, carrying patterns no one entirely understands like punctuation between cosmic sentences. Maybe intelligence isn't rare at all. Maybe it's just diffused spread thin across time, disguised as curiosity itself. When future telescopes open their mirrors to the sky, the next Vera Rubin, the next James Webb, they'll be listening not for shouts, but for whispers. Because we've learned the loudest truths rarely scream. They shimmer. One scientist put it perfectly in an unpublished paper. We don't need the universe to speak to us. We only need to notice when it's breathing. And we have. We heard it once, in the geometry of dust and plasma. Well, hear it again. Late one evening, months after the data closed, an astronomer stayed in the control room long after her shift had ended. The monitors were blank, the instruments quiet. Outside, the desert sky stretched infinitely and was cold. She whispered into the dark, "If you're still out there, thank you." The words weren't meant as transmission. They were grateful offered to a universe that had finally taught her how to listen. And in that moment, surrounded by silence thick enough to feel alive, she realized something profound. The act of paying attention is already a reply. That's how it always was. 3I, Atlas, didn't arrive to announce intelligence. It arrived to remind us that awareness is reciprocal. Every observer completes the thing. Observed. Every act of seeing becomes part of what? Seen. We were never just witnesses to the universe. We were participants in its unfolding. The cosmos isn't telling stories. It's listening for them. And we, for a brief and luminous moment, told ours. When the next whisper comes, and it won't look like what we expect. It won't arrive with answers or urgency. It will come as another anomaly at the edge of a data stream, another improbable symmetry, another pattern in the noise. And we'll recognize it instantly, not because we'll understand it, but because, remember the feeling. That quiet pull between fear and wonder, that sudden stillness when the unknown stops being a threat and becomes an invitation. The universe never needed us to believe, only to notice. It wasn't a message, but it meant something. And that meaning doesn't end here. It moves forward carried in questions, in silence, in the hands of those who will someday look up and realize they are not waiting for discovery. They are the discovery. The sky, once again, is empty. But listen closely. Something in that emptiness hums with recognition. The next whisper is already coming.